Thank you, Jared. Hello, everyone. I'm Savvinos Aristeidou, and I'm going to talk today about ground motion and correlation models as part of my PhD research. The talk is going to be divided into three main parts. First, I'm going to talk about the ground motion model, then the correlation models, and then how we can use the developed models for a more informed seismic risk assessment and demonstrate on simple stipulative vacuum systems. The initial motivation for this study was, what if we have a set of intensity measures that can have the biggest predictive power on structural response? But we saw that many ground motion models were missing or they were very limited, and the same thing for the correlation models. So we set out to develop these models and also propose ways in which they can be used. So there are various intensity measures. Traditionally, spectral acceleration is used, but FIV3 was shown recently to be an excellent IM in predicting the collapse of structures, and average spectral acceleration is shown to be well correlated with a wide range of structural response, and also duration was found to influence the nonlinear response of systems and also the collapse. The ground motion models are used to estimate those intensity measures given a set of rupture parameters. And for each ground motion model, the IM type may vary, or the database, or the regression model. So we thought of using one generalized ground motion model to avoid this heterogeneities and that can introduce bias in our risk assessment. So a generalized ground motion model can take care of the interdependencies between multiple IMs and simultaneously regress for all those IMs using a mixed effect regression, and that facilitates also ease of use. Also, the correlation models, a few correlation models are missing from the literature, which can be used for a vector-based PSHA or for a generalized conditional intensity method in ground motion record selection. And these ground motion models and predictive models of correlation coefficients were developed using artificial neural networks. Regarding the ground motion model, what is developed is it incorporates several traditional and next generation intensity measures, and it has also three different horizontal component definitions, and the performance was evaluated using several metrics and compared with other ground motion models from the literature, either with the classical approach or the machine learning methods. And this is a diagram of what I'm going to talk about in this section. Starting from the NGA-West2 database, we filtered the records to discard records that can introduce possible bias or outliers, or weak records that will not impose nonlinear demands on engineered structures. And this is a list of the filtering criteria we used. We eliminated the records with magnitude smaller than 4.5, with rupture distances larger than 300 kilometers, in recordings from free field conditions, and generally shallow crustal earthquakes. And also the aftershocks were discarded, resulting in about 4,000 ground motion records from 100 earthquakes, for which the distribution of magnitude and rupture distance and VS30 is shown in the scatter plot here. The definitions of the IM included in this model is the peak ground parameters, acceleration, velocity, and displacement, the expected acceleration for the period range shown here, the significant duration for 5 to 75% of virus intensity, 5 to 95%, the average spectral acceleration for two different period ranges, the 0.2t to 2t and 0.2t to 3t, denoted as SA average 2 and SA average 3 respectively, and the filtered incremental velocity with the period range shown here. A lot of people have asked me in the past what is FIB3. So I decided to put a slide here and briefly explain what is the definition of it and how to simply calculate it. So starting from an initial accelerogram, we apply the second order Butterworth low pass filter with a cutoff frequency FC equal to beta F, which F is the natural frequency of the system. And we use the assumption that beta is equal to the period of the system. This allows for the long periods to pass, and it filters out the short periods of the accelerogram. And then we integrate in a certain time period from t to t plus a proportion of the period of the structure, and we get the incremental velocity time series, from which we can pick out the 3 local maxima and the 3 local minima, and from those we add them, and then we get the FIB3 by taking the maximum of those 2 values. We assume, by the way, that alpha is 0.7, as suggested by Davalos and Miranda, which makes for the most efficient IM in predicting collapse. And yeah, so essentially these are the 3 highest pulses in the same direction. Also, this is a period-dependent IM because the period of the system goes into the calculations of that IM. This is a list of the predictor and response features of this ground motion model. We have 9 predictor features, and for which we give also the minimum maximum value that we have in the database, in the filter database. And those minimum maximum values also constitute the recommended usage limits of the model. And this is a list of the predictor of the response features of the IMs, and the horizontal component definition of each IM. We have a ROD 50 in geometric mean and ROD 100, so a total of 169 individual IMs we included for the output of the model. The fixed effects model architecture was the artificial neural network with one hidden layer for which the functional form is shown here. And we applied the min-max normalization for the input parameters, the log-term transformation for the vector of IMs, and activation functions softmax, tanh, and linear for the input, hidden, and output layers. The loss function was mean squared error, and this fixed effects model was passed into the mixed effects regression, so we can separate between inter and intra-event residuals and standard deviations. Then, after selecting the optimal model, and after the mixed effects, we check the performance metrics of the models, for which we present here, for the coefficient of determination as well, for the training set, for the test set, and the mean square error for the training and test set. We can see here that the performance metrics are very close to each other, which means there is no overfitting of the model, and they are at a good level to say that there is no bias in the model. Here we have the comparisons with all the different ground motion models from the literature and the IMs that these ground motion models give. And we have 2 of them are machine learning models. And here is the attenuation plots for spectral acceleration versus distance, and the magnitude amplification plots and we have 3 ground motion models here, and we can see that the fitted model captures pretty well the cloud median and is also close to the other models. Here we have the attenuation plots for significant duration for FIP3 and for SA average versus rupture distance, we can see that our model does well in capturing the median. There is a case with significant duration of the other two models. They kind of deviate from the cloud median computed here. And also it's the case also for FIP3. And the average spectral acceleration, they are more or less in good agreement. Here are the residuals of the model, which is another metric to evaluate the performance of the model. And we have here for 3 IMs as an example, for the inter-event residuals, for the intra, and for the total residuals. And we can see that there is no strong dependency on the rupture parameters, that the model presents no bias, and the homoscedasticity assumption seems reasonable. It means that the sigma stays more or less at the same level throughout the range of seismological parameters, like magnitude, distance, and VSR. This is the plot of the standard deviation of the model for the different intensity measures for this study, for the Campbell-Brosogna 14 model, which is for the SA, for the peak ground parameters, and for the indirect calculation of SA average as well. So yeah, I said here in the dispersion plot of the model. The model of Campbell-Brosogna, which is an NJ West 2 model. The model of Campbell-Brosogna for 2008 that estimates the peak ground displacement. The model of AS16, which estimates the two significant durations. So the total standard deviation of the model proposed here is kept at a low level, especially for long periods, which are the ones of most engineering interest. And as we can see, in most IMs, there is only, for example, for direct average spectral acceleration, there is only one model, the DM21, and for FIP3, there is only one model as well. So I hear you asking, why is there a need for another ground motion model? Well, this ground motion model, it developed with artificial neural networks, which is thought to give more refined predictions of next generation intensity measures, for which there are very few ground motion models to choose from, in contrast to the spectral acceleration, that there are a lot of ground motion models and very refined. So this is a step in that direction. Also, this, because it includes several intensity measures and they are regressed in the same model, it can capture the complex relationships between the intensity measures and their interactions, and it can make for a more consistent and unified treatment of IM correlations. And these next generation intensity measures can then be used for a better characterization of structural response. And the next section of this talk is the correlation models for the amplitude and cumulative intensity measures using artificial neural networks. This is the table of the IM pairs for which correlation models were developed. And in total, 24 cross-correlation models were developed. As you can see, there are the ones with the name ASO24 are the models developed here, and given also a few models from the literature that we use to compare with. The horizontal component definitions were ROT50 for the PGA, PGV, SA, and SA average, and geometric mean for significant duration and FIV3. So the methodology was no different than the other methodology to develop correlation models, starting from the inter-event residuals from each record for each IM pair. We calculate the Pearson correlation coefficient, and then with this formula, we combine the two different correlations to the correlations of the total residuals. The empirical coefficients were then regressed with artificial neural networks, which have the advantage of not needing any analytical functional forms, which don't have any physical basis, and they can often produce more difference in the observed and the predicted correlation values. And this is a schematic representation of the network for the SA FIV3 correlation model, taking as input the two periods and giving output the correlation of those IMs with two hidden layers. And this is the case of a functional form for the, this is an example of functional form for the case of one hidden layer. This is a table of the hyperparameters of each correlation model. I just wanna say that the activation functions used were linear, sigmoid, tan H, and softmax, and given is the MSE and the R square of each correlation model. Here are the results, the correlation models that we calculated, the empirical one and the predicted, and two well-established correlation models from the literature. These ones are the ones that are mainly used by, by people when they want to calculate the conditional spectrum or GCIM. So first of all, we can see that the empirical and predicted correlations are matching quite well, but this can be better appreciated in the right-hand side figure, in which slices for 4 different periods are presented, and also one additional model was added, the model of Baker and Bradley 2017, which is supposed to be an updated version of the Baker and Jayaram 2008 model. And we can see that the empirical and predicted correlations are overlapping, and the model of Akkar 2014 is more closer to the correlations proposed here. But the models of Baker and Jayaram and Baker and Bradley are a bit different, especially as the interperiod distance increases. That difference was found to be mainly because of the different filtering criteria of the database, and not because of the ground motion model or the fitting of the predictive model. This is the case of the correlation between spectral acceleration and duration, in which we see our model is about 0.1 units lower, which means that it's more negatively correlated. The SA is more negatively correlated with duration, and the model of Baker and Bradley 2017 converges to our data for longer spectral acceleration periods. This is one of the main novelties of this study, which is the correlation between FIV3 and spectral acceleration, which doesn't exist in the literature, and we can take out from this that the FIV3 is mostly correlated with medium to high periods of SA, especially for period around 1 second. And this is the case of correlation of FIV3 with duration. And we can see that it follows more or less the main trend with the correlation of spectral acceleration and duration, for mildly negatively correlated to about not correlated for high periods of FIV3. This is a case of correlation of spectral acceleration with average spectral acceleration, and is a direct correlation model which doesn't exist in the literature. And we compare here with two indirect methods, and we can see that the correlation models, the correlation models used to derive the indirect method of correlation play a big role in the correlation between spectral acceleration and average spectral acceleration, which will result in a different conditional spectrum. And also presented here is a case of average spectral acceleration with duration. Here for the correlation of FIV3 with itself, we can see that the correlation values go from 0.84 to 1, which means that the FIV3 is very correlated with itself across different periods, which makes it almost a period independent IM. And we can see here in the slices that we also have the SA correlation to appreciate how well correlated FIV3 is with itself. And here we have the correlation of FIV3 with average spectral acceleration, in which it follows also the similar trend with the one of spectral acceleration, and the case of SA average with itself. And there is already one model for this for this correlation, but the values we propose here are a bit higher. Next, I'm going to talk about how we can use this ground motion model and the correlation models for a more informed risk assessment. Generally, how can we apply those models, and how we can leverage these intensity measures for a better prediction of the response. Beginning from exploring the general trends from all the ground motions in the database, we explored the effects of significant duration and FIV3 on engineered systems. The ground motions were segregated into long and short duration and into high and low FIV3. The single degree of freedom systems used are the ones that is shown here. This is their cyclic response, and the hysteretic SM material was used. One system was non-degrading, so we didn't assign any damage values, and the other system was had cyclic and in-cycle damage due to ductility and energy, respectively. The ground motions were separated using a linear regression of SA to significant duration for the ground motions that were causing the system to go into non-linear response. And the same thing for the case of SA and FIV3. And we can see that for the system of no damage, duration doesn't have an effect. But for the single degree of freedom system with damage, the degrading one, we can see that long duration ground motion cause higher ductility demands in the system. And for the case of FIV3, even for the system of no damage, we can see that higher FIV3 results in higher ductility demands, as we can see from the deviation of the cloud means of the two. And the same thing for the system of no damage. Also, this was explored with some values from the fragility curves, in which we confirm that duration has almost no effect in the system without damage. But for the system with damage, we can see that the long duration ground motions make the system seem more fragile. And it's interesting to see how FIV3 has bigger effect in the system, in the non-degrading system rather than the degrading system. And also, it's interesting to see how FIV3 is more impactful than duration for the case of the system with damage. We can see the two damage states, the damage states 3 and 4. That is the damage states of the nonlinear response of the system. Another part of this study is checking the importance of secondary IMs, which means since we found that duration and FIV3 are important, we checked here how can they be used in a seismic risk assessment so that we can have a better constraint on the response. So we match the SA spectrum in all cases we condition on SA spectrum and on SA, and we match the secondary IMs, the duration, the FIV3, and the average spectral acceleration. And the same single degree of freedom systems were used, except with CY of 0.3 in this case. So the first thing was to conduct the PSAJ for the site of Erzincan in Turkey, and using the ground motion model that was presented before. So for different inputs, for different input ground motion selection strategies were adopted to explore how much of an effect, considering or not these secondary IMs, will make in the response, in the prediction of the response of the structure. And there was a good match of the SA spectrum in all cases. This is the case of 500 years return period for the input one. You can see that the first case is with ignoring all secondary IMs. And we can see that duration is not much. And but the other two IMs, FIV3 and average spectral acceleration, they are within the KS bounds of the GCIM distribution, which means that if we match the SA spectrum, most likely also the FIV3 and average spectral acceleration will be matched irrespective to the GCIM distribution that we have in the site. And this is the case for all inputs. You can see FIV3 is in acceptable ranges, and also average spectral acceleration, except for the duration. So MSA was conducted with each input ground motion set, and the medians and the dispersions of the MSAs were plotted here for the different IM levels and return periods. We can see that the input, they are normalized also with respect to input 2, which is the best case scenario. And we can see that all the other inputs, the median of the other inputs is different than the median of input 2. But most importantly is to observe the betas, the dispersions, in which the input 2 presents the lowest dispersion of them all. Then it's input 4, which considers only the duration as a secondary IM. And the one that gives the worst dispersion is the input 1, which is the case of ignoring all the secondary IMs. But this is the case of treating these IMs, not conditioning on these IMs, but rather matching the distributions. Here we explore how can we leverage the predictive power of these IMs by conditioning on those and not having them as a secondary IM. Because different IMs perform different levels of non-linear structural response. So the seismic demand hazard curves coming from conditioning on 3 different IMs were computed, and then the dispersion of those IMs were calculated, and they were combined in an eventual seismic demand hazard curve, which takes parts of the 3 different seismic demand hazard curves, which the parts that the dispersion of this IM is the lowest. So the first step was to perform PSAJ for each IM. This is the example of FIV3, using again the ground motion models and the correlation models that were presented before. After the MSA, we calculate the fragility curves, in which we can see that SA presents the lowest dispersion for the first 2 damage limits, then it's SA average, and then it's FIV3. So we did that for the whole range of ductilities for the whole range of displacements. And we can see here the dispersion of IM given the exceedance of certain EDP. It's first the spectral acceleration that has the lowest dispersion, then the average spectral acceleration, and then the FIV3. So these are the seismic demand hazard curves coming from each IM, and with black we can see the lowest seismic demand hazard, the lowest dispersion seismic demand hazard curve, and after we can use that curve to continue with the standard probabilistic performance earthquake engineering procedure. The benefit from this is the lower dispersion in the connection of IM with EDP, and therefore the lower annual rate of exceedance of the EDP values. To conclude, we saw a proposal of a generalized ground motion model from active shallow crustal earthquakes from a stringently filtered NGA-West2 database, which includes various amplitude and cumulative phase intensity measures and different horizontal component definitions. With this methodology, more IMs can be seamlessly added into the model with only minor modifications. And this ground motion model was validated through performance metrics and comparisons with other ground motion models. The dispersions are kept at a low level, and the performance metrics seem to be good. And from that ground motion model, the correlation models of 24 IM pairs in total were calculated. And we proposed correlation models of FIV3 that do not exist in the literature. And we saw some interesting observations I highlighted about the presentation, and direct correlation of basic average with itself and other IMs, which also doesn't exist in the literature. And the predictive models of those empirical correlation coefficients are regressed with artificial neural networks, which has not been used before for fitting IM cross correlations. And they seem to result in very good predictive models. Then we presented 3 small studies on how these models can be utilized and what can we gain in a general seismic risk assessment procedure, and how FIV3 affects the nonlinear response, how the duration, and how the matching the SA spectrum will most likely result in a good match of FIV3 and average spectral acceleration. So actively conditioning on those IMs will produce the lowest response dispersion rather than treating them as secondary IMs. And we saw that also different IMs perform differently in different nonlinear ranges, and we can combine them to produce a seismic demand hazard curve with the lowest dispersion. The models are available in GitHub, and they are soon to be implemented in OpenQuake. This is a list of journal articles that stem through this PhD research with my supervisor Gerard O'Reilly, Karin Karbali, and David Chansari.